Hey guys, this is Michael with Breaking Concepts, and today we're going to talk about discrete time models. So we've learned what is a recursive sequence previously in our different videos, and we learned about what different equations are. So we're going to use that concept, and today we're going to talk about discrete time models. So first of all, what is a discrete time model? Just by definition, you can see here, right? It is a mathematical framework that tracks the evolution of a system across distinct, separate time intervals. And just so I can make a note here, distinct, separate time intervals just means that maybe you have time of equals to 1, 2, 3, 4. It could be seconds, right? Or it could be months, or it could be years. So it really depends on the model, but the idea is that it really tracks time, okay, and is periodically, as you can see, 1, 2, 3, 4 here. So just like what we mentioned in our recursive sequence video in the past, it is what we called discrete, okay, and that's why you can see that rather than in a continuous flow. So discrete would be something like 1, 2, 3, 4. Continuous, it would be, you can have something in between. It could be 1.1, 1.5, 1.6, any even irrational number. But we don't have that within a discrete time model, which is a discrete model. Okay. So when will we really use discrete time models? Well, in biology, we use it a lot of time actually when we want to model cell division and insect population. So without further ado, let me just kind of bring that concept back in. I'm sure you guys remember from our last video, if we were to find the next term within a recursive sequence, it is basically an plus 1 is equals to our updating function, inputting an as well as equals to our an plus our difference function. So this time, using discrete time model, we're trying to model population. So instead of an, we would use n, right? N meaning population, as a population. And instead of n, we would actually use t, represents time, as we mentioned, discrete time model, right? So replace n and then with t. So not an plus 1 anymore, we use nt plus 1. And that we have the population of the next term, the next population, however you name it. So if you want to rewrite this entire thing, we would get nt plus 1 is going to be equals to our nt plus our GNT. So this is the recursive formula of how we find the next population. And once again, it also equals to FNT. And again, I can't stress this more enough. It is discrete. So just for T is equals to 1, 2, 3, 4, and so on and so forth. It is periodic. Here's an example I want to try out with you guys. So we're going to use the example of malaria parasite. So we all know that malaria is a disease spread by mosquitoes. It's spread by mosquitoes, and it is pretty bad. So it actually attacked our red blood cells. So let's look at the example here. So let's say we have a malaria parasite, and it produced 8 new parasites in a period of 24 hours, and each infected parasite goes into the red blood cells, reproduce, and burst. And the cycle goes on and on. And I have a diagram for you just to make it clear. So you can see we have one malaria parasite, and then it will go into our RBC, stands for red blood cells, and after 24 hours, it would burst. And when it bursts, there will be 8 new parasites. So let's find a general term. So let's say if someone were to ask me, how many parasites do we have in 5 days or 3 days? How would we know that? And this, my friend, is the power of recursive sequence. So let's define an NT, right? We remember NT is equals to our NT plus 1 is equals to FNT. But let's look at NT itself. NT basically, right, is the population of the time. And in science, we use something called like 0 or not, and not. And not basically means that it's the initial population of the entire thing. So what is the initial population here? Right, we'll call it the initial population, initial. So the initial population, as we know, is 1, because we only have 1. So we want to know what happens, throughout the days, because you can see the question here to give you a hint is 24 hours. So remember when I said T is a period, right? So what do you think? So what do you think the period represents here? Well, in this case, we would treat it as days, right? You have day one, you have day zero, which is the initial starting after 24 hours. You have day two, day three, day four, day five, and so on and so forth. So T right now within NT, we will call this as day. Okay, so let's do one period. One period is 1 day. So N1 is the after 24 hours. We would have a number of, as proposed here, 8. Okay, so we already have two terms. So N0 is 1, and 1 is 8. And we're given the information that every parasite would produce 8 new parasites in total. So what about the second day? What do you think is going to happen? Well, what's going to happen is actually each of them, right? We have 8 parasites, right? In each parasite, we produce 8 new parasites. So all we got to do is just do a simple multiplication, which is 8 times 8, and we got 64. So we know from day 2, we would have 64 parasites in total. But given that, we can actually use a general form to find NT plus 1. So NT plus 1, if you think about it, is just 8 times our NT. And the reason being, NT is our previous population, and it doesn't matter how big the population is, each of those parasites is going to produce 8 new parasites. So we're just going to multiply by the amount of population we have at that time. So the new period, the new day, the next day that we're going to find is just NT, which is our previous day, multiplied by 8, and then we have a total number of parasites. So let's think about what happens on day 3. So we can use this formula to kind of find day 3. What do we have in day 3? So N3 is therefore 8 times our N2. And our N2, which is at day 2, right? So 8 times 64. 8 times 64 is 512. And therefore, by the third day, we have 512 parasites within our system. Now, tying back to our idea of what a updating function was, now you can see from here, how would you define the updating function here? Well, we know updating function is just f and then inputting our current term, right? And our current term, right? So our current term is just N2. And so our updating function in this case is just 8. If we were to write function as in y equals to fx, the function would simply be f times x. That's our updating function. So I hope that makes sense with you guys. And there's a thing in discrete time model that we call a solution. Basically, a solution is a formula that helps us find NT. Because one major flaw of this equation is that if we don't know NT, we can never find NT plus 1. So we need a solution to find NT. So NT, a current population, is actually equals to our N0, our initial population, times our 8 to the power of t. Now, we have to think a little bit deeper as to how this exists. But actually, it's pretty self-explanatory here. So if we see from day 1, how many multiples of 8? There's only one 8. And for 8 and 2, we have 8 times 8. There's 2 8, right? And 8 times 8 is basically 8 squared, okay? And for this one, for N3, if you think about it, 8 times 64 is basically equals to 8 times 8 times 8. And that's just 3 times, right? That's 8 cubed, right? And so on and so forth. So you can kind of see the pattern here that this is actually the solution. The solution basically says that, okay, in order to find the population of the N period or T period, T period here, all you gotta do is multiply the N0, which is the original population, by the power of 8 to the power of t. And let's say right now I really want to know what's going to happen after 10 days. So for 10 days, all you got to do is find N10, right? Here. And then you can find, we know the N0 is basically 1 times 8 to the power of 10. And we do some calculation. So we'll get the answer of around 1,073,000,000. That's how solution works, and it's important to know how to find a solution, because finding a solution within the strict time model and recursion sequence is going to help us a lot. But note that not every recursive sequence has a solution that's that easy to find. I mean, as we progress, we can see things clearly that it is not that simple. But for this one, we have a solution which is n naught times 8 to the power of t. Now, let's talk about the solution here, the 8. The 8, well, actually, sometimes in math, we can write it as this way, n naught times rt, or nt plus 1 equals to r nt. Now, r is what we call the per capita growing factor. It is the number of offspring produced by an individual. Okay? So, and as we know from the question, it's 8, and r is super important because it's kind of dictate how our function goes and behave. But that would be a concept for another time when we talk about just a difference equation. I'll give you another example. For instance, cell division. So for self-division, you have a cell, and let's say after it divides, you will get 2, right? And after it divides, each of them is going to get 2, right? Cell division is 1 cells becomes 2, right? For, let's say, human. And now, if we recall, the T just means the period, right? I don't know if it's day or month, whatever, but I'm just going to call it as a period. All right, so we're going to start with T0, we have T1, T2, etc., etc. So in cell division, we have NT plus 1, and this time is going to be equals to 2 times NT. Right, and 2 is the updating function here, but why 2? Because, again, this is R. R would basically mean the number of offspring per capita. One parent cells produce 2 daughter cells. Yeah, so that's why we have an R of 2. And writing on this idea, if we find the solution for NT here, we can know that it's NT times N naught times the 2 to the power of T. Right? So for instance, very, very simple. What happens and how many cells after, let's say, 10 cycles of division? So again, it's N10, which is going to be N naught is 1 times 2 to the power of 10. And 2 to the power of 10, we will have 1,024 cells. So after 10 generation, we'll have 1,024 cells. This is the idea of discrete time models. We really leverage that to do model cell division and insect population. And there's many, many more different ways we can play with this. And it's going to be super helpful in our daily life. So stay tuned. Thank you.